My name is Noel Goddard. I am the CEO of Qunnect, and I have been charged not only to tell you about what we're doing with entanglement sources, but to give a small overview of entanglement sources and where the field / commercial realizations are. So I'm happy to be with you here today. As you might all know, it all starts with the source. Basically, we all know that we can't do anything in any one of the four major pillars of quantum tech, which are computing, networking, sensing, and imaging, without having high quality qubits. And that starts off with being able to have high quality entanglement. So there are many desirable features in entanglement sources, and I'll speak to a little bit of these in each one of the examples. But first, it would be great if they were on demand. Then universally, having high brightness, having high fidelity are very important. And some things which I'll speak to in some of the latter slides that are coming to light is compatible line width. And largely that's because what I've highlighted down there, device interface losses are really key as we start going away from having single quantum instrument type experiments and now talking about quantum networks, larger quantum devices like computers who are trying to interface to those networks. And then also, I think on the wish list, of course, is that these sources are directional, that you have coherent emission, and that you have good heralding efficiencies. So qubits come in many flavors, hence entanglement also is in many flavors. Entanglement is sort of the extension of the concept of superposition to multi-particle systems. On the top, I've shown two examples that you see a lot in the optical community: polarization entanglement and time-bend entanglement, which leads to polarization qubits and time-bend qubits. And I've shown them in an example of block spheres, which we've become rather used to in the quantum community, for being able to describe any combination of all the possible combinations you can have across the entire sphere worth of space. And at the surface of the sphere, you have entanglement, which actually is highly coherent. And that's really the key to being able to assure good quality quantum operations, is to assure that we're actually in those highly coherent states. Just below those optical ones, I've mentioned the OEM qubits and spin qubits, but there's also ionic qubits, charged qubits, flux qubits. I mean, they come in all different types of flavors and all need to be high quality. So the first type of source, which you'll hear some about today, I assume, are these deterministic sources. Those are not yet commercial, largely as a function of the fact that they're extremely hard to manufacture. The most common example that we know of right now are quantum dots, which are embedded in either nanostructures or films. I've shown a few examples here. These are parabolic wells, these are nanowires, and these are a film example. And what's nice about deterministic sources is that they're on demand. And that's, of course, useful for being able to use them in technological sort of experiments and applications. Also, something that's very interesting is that they're capable of having high brightness also with a high degree of entanglement, because the pair generation rate is decoupled from the G2. And all of that's useful to us in terms of thinking about how sources should be in the future. But as I said before, this is something that's been very hard to actually realize industrially. They also have narrow line widths, good fidelity. And I think one of the very interesting things which has come out of this community is that they're very tunable through being able to induce strain on any of those nanostructures. The more common one, which you see and you're going to definitely hear about from some of the providers today, are these non-deterministic sources that really come in two flavors. One is spontaneous parametric down conversion called SPDC, and the other one is spontaneous four-wave mixing called SFWM. And both of those are arguably tunable because they're two types of effects which use some type of pump lasers, which you see here on the left, in order to pump to an excited state. And depending on which one of these two that you're following, you decay from that excited state by giving off photons of either equal energy or differing energy levels. And depending on what you've actually picked as your pump lasers and the atomic levels which you're exciting, they're arguably tunable sources. For the SPDC sources, which we're seeing now on the market, one compromise is that they have rather large line widths. And we've found a number of suppliers now that are starting to narrow those with cavities. You're certainly seeing in a lot of academic papers. For the four-wave mixing type sources, the line widths are narrower by definition. However, the generation rates are a little lower than what you can get in the SPDC sources. So unfortunately, on the features list, they're not on demand because they're not deterministic. And you also have this problem that the harder that you pump them, right, you start to compromise the degree of entanglement. So they're not as good as quantum dot sources in that extent, but we do now see sources that have high fidelities. Again, the line widths are sort of all over the map depending on how you're generating the photons, but they are wavelength tunable and directional. And again, on the commercial supplier thing, this is by no means a full list, it's just a partial list, but you'll notice a lot of suppliers of SPDC, including Qubits that we'll speak later. Qunnect is in the category of the four-wave mixing. So just to give you an idea of SPDC applications, this was one of the two papers that were highlighted in the cover of Nature in early June, coming out of the Barcelona group of de Reed Martin. And in this paper, they had two separate SPDC sources that were cavity narrowed in order to couple to two quantum memories, which they entangled at telecom frequencies. In order to make this experiment work with the very high effective fidelities that they reported of 92%, they actually needed to narrow the line width of their sources to 1.8 megahertz. And it just starts to give you an idea of the challenges which are out there whenever you're trying to couple quantum instruments to quantum systems. That's exactly why Qunnect is doing what we are doing in terms of building our own atomic source, which is based on four-wave mixing. Again, we need narrow line widths. In our case, we're using atomic vapor memories that I'm going to describe in the next slide, so they're also natively compatible. And we've decided to build all of our instruments in these sort of standard drawer racks, which we're rather proud of because now we're looking towards building quantum systems. In our case, what we're very interested in is producing photons both at telecom wavelengths and at the wavelengths which are optimal for our memories. So stay tuned. And that's because it's part of our larger repeater product suite. We not only create entanglement sources, which are actively in development in our R&D labs, but we also create quantum memories. And with those two, you can start to actually host entanglement swapping protocols like I've shown here with the multi-node system, which are the basis of quantum repeating. And our flagship product at Qunnect right now is another part of that suite called a quantum memory. In our case, it's an on-demand EIT, which stands for electromagnetically induced transparency memories. This is a CAD rendering of the actual device, and we're very proud to announce that we will be shipping our first beta prototype units with the specs that you see below in September, with the hope to start producing our Mach 1 units that would be broadly commercializable in early 2022. And as I mentioned in the SPDC slide from the Barcelona group, source requirements, whenever you start to try to couple sources to memories or sources to any other quantum devices, are really important. In our case, we have very narrow line widths that are demanded by EIT, and also wavelength specificity because we have specific wavelengths in which our memories function best. So this is one of the reasons at Qunnect that we spend time developing sources, because I want our sources to be highly efficient with our memories. So if you'd like to learn more, please go to qunnect.inc. And if you happen to be passing through New York, we are located in the Brooklyn Navy Yard, just across from Manhattan. We'd love to show you what we're up to. And thanks so much for the opportunity to speak today.
Noel, you actually, wow, you presented that you're actually shipping, you're selling and shipping quantum memory. I'm not aware of anyone in the United States that's doing that yet. I could be corrected, but can you care to comment on that?
Thanks. That's a really exciting moment for our company. So yes, we are shipping. It's the beta prototype, but we're incredibly proud of it. As Chris Monroe was mentioning in his talk, I mean, I think one of the things that we all understand is that the key to connecting quantum processors are versions of quantum networks. And of course, the goal of those being, at least in longer distances, to actually do quantum repeating. And what we're doing is building out the core units for a quantum repeater product suite. And the two things are memories and sources when you start talking about quantum instruments. So yeah, we're very proud. I think, so to our knowledge, we're actually the first memory suppliers globally. So exciting times.
Right, and you're actually saying that you're going to have, so you have your beta shipping next month, but you're actually going to be, you think, almost to or at TRL level 3 in December with the same product, right?
Correct. So we're basically, I know that I went through that slide quickly, but the difference between the beta units and the final units is that I think what everybody knows here probably in the quantum world is that it's one thing to be able to produce a product, it's another thing to be able to really nail it on stability. And Qunnect has been working hard to get all of the engineering elements correct on our instrumentation so that these things can start to be plug and play. And Mark 1 is really intended not only to perform slightly better than the Mark beta units, but significantly better on the stability and the engineering side.
Great, thank you, Noel. Chris and Steve, do you have any questions for Noel on that quantum memory?
Sure, this is Steve. One question would be, Do you see people using it for something else besides a repeater? What other uses do you see?
This goes back to, there always will be academic customers. So I think the broad answer on that is yes for academic customers, because they may only want to use it also for the classical part of the memory and not necessarily the quantum aspect. But the other thing is that quantum memory really has sort of two functions, right? One could be literally just to serve as a data buffer timing element within a larger network. So, I mean, anytime you need to buffer the rate at which data is going from one point to the next, you could have a standalone quantum memory standing somewhere in the network, or it could be as part of one of these larger multi-node systems that becomes a repeater.
Thank you.
Yeah, I have maybe more, I don't know if it's a question or a comment, but I could see kind of two directions for you to go into hardcore quantum computing this way. One, maybe harder, is to use the individual atoms. I think you have a vapor cell type model there. Yeah, to somehow get them to interact, maybe with Rydberg states and so forth. That's probably more academic. But maybe more interesting is the linear photonics version of quantum computers. They desperately need memory.
Yes.
Instead of circulating photons around and so forth. Do you look forward? I mean, if your system is a real commodity and you can just plug and play, like you say, I mean, I could see a real opportunity there. That's maybe more of a comment. I know you're going to agree.
No, of course, we appreciate that. So I can tell you that, so everything we do is vapor cells. So definitely the memory itself is a warm vapor cell, but then we also have our sources are vapor cells, our frequency locks are also vapor cells, but the sources also, in the way that you define them, right, can also be used in different configurations to be more like frequency converters, which you referred to earlier. And we certainly believe that one of the next major steps, both with our company and I think other companies that are starting to come online, is to look at how one is going to connect the quantum computers to the quantum networks.